special importance is one special case of nth roots of unity, which is the cube roots of unity, and so we are going to study that. Why? Because a lot of expressions have cubics in them, and especially the cubic polynomial is the polynomial that comes after the quadratic polynomial, and therefore the solution of cubic polynomials many times involves the cube root of 1, or at least numbers which have cube root of 1 attached to them, and that is why it is important to study cube root of 1. So let us look at how to find the cube roots of 1 and what their properties are. Suppose I have z cube is equal to 1, again as usual. So therefore z will be equal to the number 1 raised to the power of 1 by 3, right? So z cube minus 1 is equal to 0, and I factorize it by taking 1 as just 1 cube. So therefore this gives us z cube minus 1 cube is equal to 0. So factorizing that, I get z minus 1 times z square plus z plus 1 is equal to 0. So therefore we get z is equal to 1, and the other part, the other factor is a quadratic factor, and applying the quadratic formula we get minus 1, the coefficient of the z, plus minus square root of 1 square again, minus 4 times the coefficient of z square times the constant term, divided by 2. 1 square is 1, 1 minus 4 is 3, 1 minus 4 is negative 3, and so we have minus 1 plus minus the square root of 3 times the square root of minus 1, so we write that as iota divided by 2. So therefore we are getting two imaginary values as expected for the z. One is minus half plus root 3 by 2i, the other is minus half minus root 3 by 2i. In fact, as it happens, if you square one of these, you'll get the other one. So if I square minus half plus root 3 by 2i, I'll get minus half minus root 3 by 2i. So therefore, if I take this as omega, I don't need to find a new symbol for the other one. I can just write that as omega square. So therefore, the cube roots of 1 are the real number 1 and the two imaginary numbers omega and omega square. So as promised by the fundamental theorem of algebra, we get 3 roots for the cube root of 1, just that the other 2 roots are imaginary roots and 1 is the only real root. What are the properties of the cube roots of unity? Well, first thing, of course, that the products of the cube roots of unity will be equal to, of course, 1 into omega square. 1 into anything is that number. Omega times omega square is omega to the power of 3. And since omega is a cube root of unity, when I cube it, I get 1. So therefore, most important thing to remember, omega to the power of 3 is equal to 1. And not just this, omega to the power of any multiple of 3 is also going to be equal to 1, where k is an integer. So it does not necessarily have to be a positive integer only. You can have omega to the power of minus 12. 1 by omega to the power of 12 is also equal to 1. So therefore, omega to the power of 3k is equal to 1, and therefore omega to the power of 3k plus some other integer, say r. Now this can be split as omega to the power of 3k times omega to the power of r. Omega to the power of 3k we just saw is equal to 1. So omega to the power of 3k plus r, you might as well just write it as omega to the power of 3. Omega to the power of r. Okay, so for example, omega to the power of 17. Now 17 is 2 exponents more than 15, which is the nearest multiple of 3 that you can think of. Of course, 18 is there, but then for 18 you'll have to come backwards, which will involve a negative exponent. So to avoid that, you can write it as omega to the power of 15 plus 2, and omega to the power of 15 is 1. So therefore, omega to the power of 17 is equal to 1 multiplied by omega square. So therefore, omega to the power of 17 is the same thing as omega square, one of the cube roots of unity. In fact, any power of omega will be one of the cube roots of unity. Either it will be 1 or it will be omega or omega square. Next property, the sum of the cube roots of unity is equal to 0. This, as we have looked at it in the general form, nth roots of unity, the sum of nth roots of unity always equal 1. So this also forms a geometric series, and you can substitute the values of omega and omega square and see that they add up to 0. Property 2 is that, as we have seen, the nth roots of unity also add up to 0. And so, as a special case, the cube roots of unity also add up to 0. Nothing much in it. You can just substitute the value of omega and omega square and actually verify that they mathematically or numerically add up to 0. The products of cube roots of unity is equal to 1. We've already seen this. Each complex cube root of unity is a reciprocal of the other. Okay, how is that? We know that omega cube is equal to 1. And omega cube can be split as omega times omega square is equal to 1. So we have omega is equal to 1 by omega square, and omega square is equal to 1 by omega. The cube roots of minus 1 now will be minus 1 minus omega square. How? We just let z cube be equal to minus 1. So z cube plus 1 is equal to 0. Z cube plus 1 cube is equal to 0 because 1 can always be written as 1 cube. Factorize that, and so you'll get one of the factors as z plus 1, which corresponds to z is equal to minus 1, the minus 1 that we expect as the cube root of minus 1, and of course a quadratic expression will be there, z square minus z plus 1 is equal to 0. Solving that, you will get the roots as minus omega and minus omega square. Always, when n is a multiple of 3, 1 plus omega to the power of n plus omega square to the power of n will be equal to 3. And when n is not a multiple of 3, 1 plus omega to the n plus omega square to the n will be equal to 0, corresponding to that property that we just discussed. Now, there are some important algebraic expressions, some algebraic identities which can be written in terms of omega and omega square. For example, I can write omega cube plus a cube plus b cube as a plus b times a square minus ab plus b square. That expression a square minus ab plus b square, we were always told, is not factorizable, right? But it is factorizable if you can take omega and omega square. So you can write that as a plus b omega and a plus b omega square. A cube minus b cube is equal to a minus b times a minus b omega times a minus b omega square. And a cube plus b cube plus c cube minus 3abc is equal to a plus b plus c times a square plus b square plus c square minus ab minus bc minus ac. We've always been told that the other longer expression is not factorizable. Well, it is. You can write that as a plus b omega plus c omega square times a plus b omega square plus c omega. So therefore, a cube plus b cube plus c cube minus 3abc falls neatly into 3 brackets, a plus b plus c times a plus b omega plus c omega square plus a times a plus b omega square plus c omega. So these are the important properties of cube roots of unity. Cube roots of unity, as we have discussed about nth roots of unity, can also be represented on our Argand plane. They form the vertices of a equilateral triangle with one vertex at the point 1, 0 and the other 2 vertices at 120 degrees intervals, as we have seen here. Okay,